Students, I welcome you all for the second lecture on NMR spectroscopy. In the first lecture, we saw the magnetic properties of nuclei. I told you we have some special nuclei in organic chemistry, organic molecules. They have some special properties. That is, they have the magnetic properties because of the presence of odd number of neutron, odd number of electron, proton or both. So if any nuclei has odd number of neutron, proton or both, then it has the special property, namely it has a magnetic property. So if the number of nucleons is odd, that is the odd number of proton or neutron, then the spin value is given by the formula I is equal to half n. Suppose if the atomic number is even and the mass number is also even, so that means if you have even number of protons and neutrons, then n is equal to 0, it has no spin. Example is carbon 12. If you have a nuclei of hydrogen, then it has only one proton. Deuterium has one proton and one neutron, so its n value is 2. So spin value I is equal to 1 for deuterium. For hydrogen, n is equal to 1, so spin value I is equal to 1. I is equal to 1 by 2. And we have many nuclei like that, F19, C13, P31. So all these nuclei have spin value I is equal to half because they have odd number of protons or odd number of neutrons in some cases. So if a nuclei has spin value I is equal to something of 1, 3 by 2, 2 like that, then it has a angular momentum because of the spinning charge that is present in the nucleus. If you place such nuclei over the magnetic field, then because of the spinning charge, the nuclei gains the magnetic moment, that is called as the nuclear magnetic moment. It is expressed by the symbol mu. So if you place such a nuclei having magnetic properties in a magnetic field, then it has different orientations. The number of orientations shown by the nuclei is given by the formula 2i plus 1, where I is the spin value. For a nuclei of hydrogen, I is equal to 1, so 2 of is equal to 1, 1 plus 1, 2. A nuclei of hydrogen has two orientations when it is placed over a magnetic field. Any nuclei, if it has a spin value I is equal to half, then it will have two orientations. Suppose if you have a nuclei whose spin value I is equal to 1, for example deuterium, then 2 into 1 plus 1, 3 orientations are possible for a nuclei of deuterium. So the number of orientations assumed by a nuclei when it is placed over a magnetic field is given by the formula 2i plus 1. It depends on the spin value I. The spin value is again depends on the presence of odd number of neutrons, protons or both in the nuclei. So this just I want to recall. Let us go to the other slides also. So we have these nuclei. Everything I have explained already. So the nuclei, when it is placed over a magnetic field, it is present in the lower state. It can be promoted to the other orientation, that is the high energy state. This is called as the quantization of energy. In quantum mechanical terms, I can say this is called as the quantization of energy. So the energy required for the promotion of a nuclei from the lower state to the higher state is given by the formula E is equal to h nu, and again E is related with other parameters, namely magnetic moment, h0 applied field, and the spin value E is equal to mu h0 by I. If we equate the two equations, then we have the equation nu is equal to mu h0 by hi. You can see the two orientations. See, applied magnetic field is the upward arrow, another upward arrow, that is the aligned orientation for the nuclei, and downward arrow is high energy state. It is where the nuclei is opposing the applied magnetic field. Let us go to the other slides also. See, I told you that the nuclei is having two orientations when it is placed over a magnetic field, when its spin value I is equal to 1. Spin value I is equal to half. So a nuclei of hydrogen will have two orientations. Now how can we promote the nuclei from the low energy state to the high energy state? We must find a mode by which we can give the energy to the nuclei. I explained it with the spinning top example. So nuclei has a precessional frequency. If we irradiate the nuclei with the precessional frequency, then it will go to the excited state. And the nuclei is remaining in the excited state. It is how this can also be explained by other slides. See, the precessional motion. You apply another magnetic field or radio frequency source with the help of another magnetic field source. You are applying the frequency which is equal to the precessional frequency. So the nuclei goes to the excited state. See, we can see the promotion of nuclei from the low energy state to the high energy state. See, in the clockwise direction it is aligning, in the anti-clockwise direction it is opposing. This is also a representation. So spin orientation of the nuclei: hydrogen H1C13, F19, P31. These are some of the nuclei which has a spin value of. So when I is equal to 1 by 2, then the number of orientation is 2. See, these are the two possible states. You can promote the nuclei from the ground state to the excited state. For that you require energy, and we saw how the energy can be injected, and we saw the energy that is required in a magnetic field of 1.4 Tesla or 14,092 Gauss. See, a frequency of 60 megahertz is required for some nuclei. For some nuclei it is requiring 80 megahertz, 100 megahertz, 240 megahertz, like that. So I explained you the methods of recording NMR spectroscopy also. There are two methods. One is your field sweep method, and another one is the pulse method. In field sweep method, we vary the applied magnetic field. Slowly we vary the applied magnetic field, and as a result the nuclei will come to resonance one by one. You are having a fixed source whose frequency is 60 megahertz. So if you irradiate the sample with 60 megahertz, because of the variation in the magnetic field, slowly all the nuclei will come to resonance one by one. They will be promoted to the excited state. You will get a signal and you can record the NMR spectrum. So based on the frequency of the fixed source, we have different instruments, namely 60 megahertz instrument, 100 megahertz instrument, 240 megahertz instrument, 400 megahertz instrument, like that. In pulse method, you are not varying the magnetic field. You are fixing the magnetic field H0, that is the applied field. What happens? The different nuclei are in different environment. Their magnetic moment values will vary. So as a result, the precessional frequency will vary, and they will require different types of frequencies to go to the excited state. So there will be variation in the frequency of the nuclei that is present in the organic molecule when you are fixing the applied magnetic field H0. Now you can easily promote all the nuclei to the excited state. This is done by the modification of the radio frequency source. Instead of one source, you are having a pulse. The radio frequency source will have all the frequencies. It is a broadband. It will have all the frequencies. So all the nuclei present in the organic molecule will be promoted to the excited state immediately or all of a sudden, and you will get the NMR spectrum also. So this is your pulse method. The NMR spectrum can be recorded by two methods. And in the last lecture, we stopped with a question. What happens to the nuclei in the excited state? See, we are studying the transition of the nuclei in NMR spectroscopy. Nuclei having special magnetic properties are promoted from the low energy state to the excited state. Because of this excitation, can we get a signal? Can we get some information from the structure of the molecule? See, the nuclei which is going to the excited state cannot remain there. It will lose its energy and it will return to the ground state. If it returns to the ground state, then the nuclei will be again promoted. So, there should be a continuous promotion of the nuclei from the ground state to the excited state. And in the excited state, the nuclei should lose its extra energy and it should return to the ground state. Continuous. This should be a continuous process. See, if the nuclei loses its energy in the excited state and if it comes to the ground state, then the nuclei the number of nuclei in the ground state will be more than the number of nuclei in the excited state. This is called as the population difference or population level. You might have studied, you may study all these things, how to calculate the number of nuclei in the ground state and the as state using the Boltzmann statistics equation in physical chemistry spectroscopy. You have calculations also. See, the nuclei loses its energy in the excited state and returns to the ground state. Because of that, the number of nuclei called as the population of the nuclei in the ground state is more than the excited state. But the nuclei goes to the excited state continuously because of the injection of electromagnetic radiation. So it should be a continuous process. And the population should be higher in the ground state than in the excited state. If it is clearly observed, then only you will get a signal in the NMR spectrum and you can record the NMR spectrum and you can get some structural information. So the nuclei in the excited state loses its extra energy and this process is called as the relaxation process in NMR spectroscopy. See? The nuclei loses its energy in the excited state and it returns to the ground state. The process by which the nuclei are losing the energy is called as the relaxation process. So, if the nuclei undergoes relaxation, then the population of the nuclei in the ground state is more than the excited state always. The NMR spectrum the signals can be continuously received and you can record the NMR spectrum. Now, let us see what is this relaxation process or how this relaxation process occurs. See, the relaxation process occurs by two methods. See, the nuclei are having the spin. It is because of the magnetic moment. So the nuclei continuously spins when it is placed over a magnetic field. If the spin is transferred to another nuclei, then the first nuclei comes to the ground state. It is getting relaxed. So we call this process as relaxation process. So the promoted nuclei, how it loses its extra energy happens by two processes. One is called as spin lattice relaxation and another one is called as spin-spin relaxation. What is this spin lattice relaxation? See, the organic molecule may have some 3 or 4 carbons. If it has 3 or 4 carbons, then each carbon may have at least 1 or 2 hydrogens. See, I have given one example. See, the proton which is in the box, is excited. It is having the spin. It is in the excited state. Now, if the spin is transferred to the remaining part of the molecule, that is called as the lattice. If the spin is transferred to the remaining part of the molecule, it is called as the lattice, and this process is called as spin lattice relaxation. So the organic molecule may have 3 carbons, 4 carbons, 5 carbons, even 1 carbon, methane. If one hydrogen is promoted, the remaining 3 hydrogens are in the, if they are in the ground state, that can be transferred. The spin of one excited proton can be transferred to the remaining 3 protons. So it is spin lattice relaxation. The spin lattice relaxation is also called as longitudinal relaxation. So there is another name for this spin lattice relaxation process. See, the other one is spin-spin relaxation. What is the spin-spin relaxation? See, you may have a molecule where one proton is having the higher energy, or it is existing in the high energy state. You have another molecule where one proton is remaining in the ground state. Now, because of molecular collisions, the spin of one proton can be transferred to another proton. This is called a spin-spin relaxation or transverse relaxation. So, in spin-spin relaxation, the energy or spin of one proton in one molecule is transferred to the proton of another molecule. This relaxation is called a spin-spin relaxation or transverse relaxation. So, the relaxation process is of 2 types. One is spin lattice relaxation and another one is spin-spin relaxation. Spin lattice relaxation is also called as longitudinal relaxation, and spin-spin relaxation is also called as transverse relaxation. What happens in spin lattice relaxation? The spin of a magnetic nuclei is transferred to the remaining part of the molecule, the protons which are present in the remaining part of the molecule. So that is your spin lattice relaxation. In spin-spin relaxation, the spin of a proton in one molecule is transferred to the proton that is present in another molecule due to molecular collision. This is called a spin-spin relaxation or transverse relaxation. So we have 2 types of relaxation process. See, we have just seen what is the relaxation process. The nuclei is in the excited state. If it loses its energy, it goes to the ground state. This process is called as relaxation. The relaxation takes place by two ways. One is spin lattice relaxation and another one is spin-spin relaxation. The time taken by the nuclei in the excited state to lose its energy and return to the ground state is called as the relaxation time. It is indicated by the time symbol T, small t. See, relaxation time is a very important term in NMR spectroscopy. Later on I will explain certain facts using this relaxation time. So relaxation time T is the time taken by the nuclei to return to the ground state from the excited state. Suppose if the relaxation time is very short, then what happens? If the relaxation time is very short, T, if it is very short, then the signals are very broad in NMR spectroscopy. So, if the relaxation time is longer, then the signals are very clear and the signals are continuously observed. See, if the relaxation time is very short, then the nuclei going to the excited state returns to the ground state quickly. Again it goes, again it comes. So the signals are very broad. The NMR spectrum cannot give some useful information about the protons and the environment of the protons in organic molecule. Whereas if the relaxation time T is sufficient enough, longer enough, T should be longer enough, then the signals are very clear and continuously observed in NMR spectroscopy. So in PMR spectroscopy, proton magnetic resonance spectroscopy, the time taken by the nuclei is longer, so we are able to get some information about the structure of the molecule. See, if the nuclei undergoes relaxation, I told you there are two ways. One is spin lattice relaxation and another one is spin relaxation. Out of the two, the spin lattice relaxation process takes longer time. So, if the spin lattice relaxation is very longer, then the relaxation time is very longer. The nuclei spends sufficient time in the excited state and then return to the ground state. Because of that, we are getting a signal. So, this is about the relaxation time in NMR spectroscopy. See, the next slide is about the instrumentation in NMR spectroscopy. Here, you can see the central part. In the central part, you can see that a glass tube. So the glass tube is having the sample where you can have the organic compound for which the spectrum can be recorded. See, the sample tube is, this is approximate instrumentation diagram, just a outline sketch only. You can see a coil that is wounded around the glass tube. Okay, see, that is connected to the radio frequency transmitter. That is the source, the external source that will give you the magnetic field. So radio frequency transmitter that will supply the frequency that will match with the precessional frequency, and the nuclei will go to the excited state. So radio frequency transmitter. And here you have the sweep coil, that is your magnetic field. That is for generating magnetic field, sweep generator, sweep coil, sweep generator. And here on the right side you have the radio frequency receiver and detector. What are the frequencies that are absorbed? What is the frequency that is left over? That will be received and detector, and you have the printer, XY plane. So everything is maintained by microprocessors. So it is a purely an electronic instrument, and we are having a record of this one, record of the NMR spectrum. So this is about the instrumentation. Here I want to specify one important point. See, the glass tube, I indicated it with the arrow mark. That means the glass tube is spinning in that direction. What is the reason? See, you are applying a magnetic field and you are sending the radio frequency waves which are having the precessional frequency in one direction only. So, the molecule which are facing that direction will be promoted to the excited state. The sample will not experience the external magnetic field uniformly. So, to experience the external magnetic field in a uniform manner, the sample tube is in a constant state of rotation. We have a rotator. In the instrument, we have a rotator. I had a chance once in my lifetime to look the NMR instrument and its functioning in Hindustan Photo Film Factory, Ooty. I had a chance once. I visited the Hindustan Photo Film Factory. There I saw the 400 megahertz instrument and how the NMR spectrum is recorded in a 400 megahertz instrument in Ooty, Hindustan Photo Film Factory, Ooty. So, the sample tube is in a constant state of rotation. Continuously it is rotated with the help of your rotor. Then only it will experience the magnetic field uniformly. And the signals are received by the receiver and you are having the plot, XY plot or the NMR spectrum. See, this is about the energy that is required. The frequency of absorption is given by the formula nu is equal to mu h0 by hi. Already I have told this equation. Energy required for the promotion of nuclei from the ground state to the excited state is given by the formula E is equal to h nu, and the same energy is related with the formula E is equal to mu h0 by I. Mu is your magnetic moment, h0 is your applied magnetic field, and I is your spin value. Now if you equate the two equations, left hand side is the same. If you equate, then h nu is equal to mu h0 by I. So nu is given by, you will bring down the h. If you bring down the h, nu is equal to mu h0 by hi. H is Planck constant. So clearly we can say that in NMR spectroscopy, the frequency of absorption of a magnetically active nuclei having magnetic moment mu in a applied field strength of h0 is given by the formula mu is equal to mu h0 by hi. Mu is the magnetic moment of that nuclei, h0 is the applied field strength, h is Planck's constant, and I is the spin value. See, here I have given two examples. One is an atom of hydrogen and another one is an atom of deuterium. Hydrogen atomic number 1, so you have one proton. To neutralize that one proton, positive charge, protons are having positive charge. That is why the nuclei is spin. Nuclei spins in a magnetic field if it has odd number of protons. Okay, so because of the charge of the nucleus spins when it has odd number of proton or neutron. So to neutralize the positive charge of the proton, you have one electron in the outer electronic atmosphere. Consider the atom of deuterium. It has one proton, one neutron. So in addition to one proton, you have one neutron also. The number of nucleons is 2. So spin value I is equal to half n. N is equal to 2 here. So I is equal to 1. I is equal to half for hydrogen. I is equal to 1 for deuterium. Deuterium being an isotope of hydrogen, you have atomic number 1. So one proton, it is balanced by one electron in the outer electronic atmosphere or in the outer orbital. Now, a question rises. See, you are applying a magnetic field H0. When you are applying a magnetic field H0, whether the magnetic field applied H0 is fully felt by the nucleons in the nucleus. This question is raised. Because when you speak about the atom having a special magnetic property, in the atom you have neutrons, protons in the nucleus. The positive charge of the nucleus is neutralized by the outer electronic atmosphere. So you cannot leave the electronic atmosphere that is present outside the nucleus. When you are applying a magnetic field H0, the outer electronic atmosphere, the outer atomic orbitals which are having the electrons, they will prevent the applied magnetic field to some extent. So we are applying a magnetic field H0. The magnetic field is not fully felt by the nuclei. So here the magnetic field that is felt by the nuclei depends on the outer electronic atmosphere. It is purely based on the atomic number. If you have atomic number 1, one proton and one electron will be present in the outer atmosphere. For carbon, atomic number is 6. 6 protons are present and 6 electrons are present in the outer atmosphere. And for fluorine, atomic number is 9, isotope of fluorine, F19, 10 neutrons, 9 protons. So to neutralize the 9 protons, you have 9 electrons in the atomic orbitals. P31, 15, 16, proton, neutron, 15 electrons are present in the outer atomic orbitals. So, the shielding effect also varies from one nuclei to another nuclei. So, the extent of magnetic field, you are applying a magnetic field H0, the extent of magnetic field experienced by the inner nucleons varies because of the shielding effect offered by the electrons in the atomic orbitals. So, we modify the expression. The applied magnetic field is H0, but the actual magnetic field experienced by the nuclei is H is equal to H0 into 1 minus sigma. Sigma is a new parameter. It is called as the shielding parameter. Sigma is your shielding parameter. I told you the shielding of the nuclei differs from one nuclei to another nuclei. It is depending on the atomic number or the number of electrons present in the outer atomic orbitals. So the actual magnetic field experienced by a nuclei is given by the formula H is equal to H0 into 1 minus sigma. Sigma is your shielding parameter. So H is the actual magnetic field that is experienced by the nuclei. H0 is the applied magnetic field. So we have to modify the expression. The frequency of absorption of a nuclei in NMR spectroscopy is given by the formula mu is equal to mu H0. Originally it is now modified by H, mu H by Hi, small hi, and H has to be substituted. H is equal to H0 into 1 minus sigma. So you have the expression mu is equal to, the frequency of absorption is given by the formula mu is equal to mu H0 into 1 minus sigma by Hi. The new parameter is your sigma, where the value is called as the shielding parameter. Now, let us move to the other aspects of NMR spectroscopy. So, we saw the various methods by which the NMR spectrum can be recorded. I told you that the nuclei, when they are placed in a magnetic field, will show different precisional frequencies. So the NMR spectrum can be recorded in two ways. One is your field sweep method and another one is your pulse method. Now do you understand the reason why the nuclei are varying in their spinning frequency or precisional frequency? See, one reason is due to their magnetic moment and another reason is due to the shielding parameter. So in field sweep method, we vary the magnetic field and the frequency of absorption is fixed by the radiation source. You are fixing the radiation source as 60 megahertz, 100 megahertz, like that. So the NMR instrument is also called by the name 60 megahertz or 100 megahertz. See, the pulse method, here you have the magnetic field at a constant value. So H0, the applied magnetic field, is kept constant and the frequency is varied. So if you irradiate the nuclei with a pulse containing all the frequencies, then the nuclei will undergo excitation. In NMR spectroscopy, I used to recall the points then and again. Then only you can understand the matter clearly. See, we now saw two methods by which the NMR spectrum can be recorded. One is your field sweep method and another one is your pulse method. And I told you, you can vary the magnetic field H0 also. So one can record the NMR spectrum at 1.4 Tesla or 14,092 Gauss. Suppose one man in United States, a scientist in United States, record the NMR spectrum of a molecule and he publishes the data. if you record the NMR spectrum for a molecule, namely ethyl bromide, let us consider ethyl bromide or bromoethane is recorded in NMR instrument by a scientist in USA with the help of a magnetic field of 2 Tesla, and he uses the pulse method. The magnetic field is fixed by him at 2 Tesla, and he uses the pulse method for recording the NMR spectrum, and he publishes the data. The frequency of the two types of nuclei in bromoethane, CH3, CH2, Br, the methyl protons and CH2 protons, they will show different values, and you will get the data. Suppose for the same molecule, if another scientist records the NMR spectrum, by varying the magnetic field and by fixing the radio frequency source at 60 megahertz, his data will be different from the data published by a scientist from USA. And another one records the NMR spectrum of bromoethane in field sweep method also, but the frequency chosen by him is not 60 megahertz, it is 100 megahertz. So, because of this variation in the methods of recording NMR spectrum, we will have plenty of data, and if data accumulates for one molecule, we have different types of data. Okay, we will get the structural information. The structural information can be given by the scientist, but the data will be different. Suppose if you go according to the data and if you make a comparison with the data, it will lead to confusion. So, the scientists who worked in NMR spectroscopy, we have a group of chemists who are working in NMR spectroscopy alone. Okay? So, after seeing the volume of NMR spectral data, they thought of proposing a universal unit for the frequency of absorption. See, the data should be uniform. Whether a scientist is recording the NMR spectrum of bromoethane according to field sweep method or in pulse method, whatever may be the method of choice, in pulse method, if the magnetic field is 2 Tesla or 1.4 Tesla, whatever it may be, in field sweep method, whether the frequency of the external source is 60 megahertz, 100 megahertz, 240 or 400 megahertz, whatever it may be, the frequency of absorption should be uniformly expressed. So how can we do that? So the first step for the derivation of the universal value for a proton in NMR spectroscopy is achieved by comparing the frequency of absorption of an organic compound with a reference compound in NMR spectroscopy. See, we know the chemical shift value of the reference compound. They have chosen a reference compound. This compound will be used as a reference compound for recording any kind of compound in any kind of instrument in NMR spectroscopy. So, with reference to that compound, we can, if we calculate, we have the instruments, microprocessors. The instruments for NMR spectroscopy were modified, and we are able to compare the reference compound and its absorption with the organic compound for which we have to record the NMR spectrum. So from that data, by a compared data, we are able to arrive at a universal value for the frequency of absorption of the organic compound for the different protons. First, let us see the reference compound that is used for the for recording the NMR spectrum. It is very important. In B part question, people may ask you, what is the reason for selecting this one as a reference compound? The reference compound that is used in NMR spectroscopy is your tetramethylsilane. In the periodic table, we have carbon. After carbon, we have silicon. So just like carbon, in the column, carbon, silicon. Below carbon, we have silicon. Just like silicon, carbon, silicon also shows a valency of 4. And it is also covalent in nature. So silicon forms a tetravalent molecule, namely tetramethylsilane. 4 methyl groups are attached to a silicon molecule, silicon atom. Tetramethylsilane, TMS, abbreviated as TMS, first 3 letters. TMS. So tetramethylsilane is the reference compound in NMR spectroscopy. This is the structure of tetramethylsilane. See, in tetramethylsilane, you have 4 methyl groups. Each methyl group has 3 protons. So 4 into 3, 12 protons are there. And that too, the 4 methyl groups are in the identical environment. They are same, exactly identical. So all the 12 protons will give only one signal in NMR spectroscopy when they are placed in a magnetic field. So if you look at the NMR spectrum of an organic compound which is recorded along with tetramethylsilane. Tetramethylsilane is the reference compound. It should be added. So to the sample tube containing a solvent in which the organic compound is dissolved, the tetramethylsilane, few micrograms of tetramethylsilane, okay, that is also added. So the signal for tetramethylsilane will also appear in the NMR spectrum. And the signal can be easily identified because tetramethylsilane has 12 protons in one environment. The intensity of the signal will be the maximum. From that you can easily identify tetramethylsilane. So with reference to the signal of tetramethylsilane, the frequency of absorption of other protons in the organic molecule will be plotted. Okay. So from the plot we are able to distinguish the organic compound and its signal. And this plot will be the same whether you are recording the NMR spectrum for a organic molecule either in a pulse method or in field sweep method, either in a 60 MHz instrument, 100 MHz instrument, or whether in a 1.4 field Tesla magnetic field or 2 Tesla magnetic field, whatever it may be. Since you are recording the signals relatively in comparison to tetramethylsilane, the relative comparison and the relative record of the NMR spectrum will be the same, whatever may be the method of NMR spectrum and its recording. So tetramethylsilane is the reference compound. See, tetramethylsilane is chosen as the reference compound for various reasons. Let us see the reasons one by one. See, I told you that silicon is in the family of carbon. Carbon is electropositive, we know that. So as we move, carbon is electropositive, the next member is silicon. Silicon is also electropositive, and the electropositivity of silicon is more than carbon. If you go down, the electropositivity increases. If you go from left to right in the group, in the horizontal direction, left to right, then the electronegativity increases. Carbon is less electronegative than nitrogen. Nitrogen is more electronegative. Electronegativity increases if you move from left to right. Whereas if you move from top to bottom, then electropositivity increases. All these things we will study in the periodic properties of elements when we study about the periodic table. So electronegativity increases as we move from left to right in a periodic table, whereas electropositivity increases as we move from top to bottom in a period. So in the carbon group, silicon is more electropositive than carbon. There is an advantage of choosing silicon compound as the reference compound. So silicon is highly electropositive. As a result, what happens, the frequency of absorption of the protons which are attached to the methyl group and that is attached to a silicon will be different, definitely. So the frequency of absorption of the 12 protons will be different from the protons of the organic molecule. Whatever may be the type of organic molecule, the signal will be different. Carbon containing organic molecule. Because tetramethylsilane is a silicon containing organic molecule. So silicon is highly electropositive. The 12 protons are in a totally different environment. So their frequency of absorption will be different. Apart from that, tetramethylsilane is highly volatile. Suppose if you record the NMR spectrum by dissolving it in a suitable solvent. Later on we will discuss about the solvents that are used in NMR spectroscopy also. So if you make use of a suitable solvent, the solvents are very costly. That is why the recording of NMR spectrum is expensive. If you go to a sophisticated instrumentation center and if you want to record the NMR spectrum, depending on the type of NMR spectrum, they may charge you. If it is a high resolution spectrum, 400 megahertz means they may charge you around above 1000 rupees or around 2000 rupees. For one spectrum they may charge. Suppose if you want to recover the organic compound after recording the NMR spectrum, then the compound can be recovered by dissolving it in a the compound is dissolved in a volatile solvent. The compound can be recovered from the solvent by vaporization. If the compounds are highly volatile, you can easily recover them. So TMS is highly volatile. It can be easily vaporized. So the organic compound can be easily recovered. The organic compound for which you want to record the NMR spectrum. So tetramethylsilane can be easily recovered. Tetramethylsilane is also an expensive compound. It can be used for recording the NMR spectrum later. So the recovery of the organic compound as well as the reference compound tetramethylsilane both are easy. For this reason also tetramethylsilane is chosen as the reference compound. And another important thing is tetramethylsilane being highly covalent in nature because of the electropositivity of silicon. See, carbon family member. So it also shows covalency and it is not reacting with other organic compounds. So TMS is not reacting with other organic compounds. Because of this reason also TMS is chosen as the reference compound. And TMS has 12 protons, so the signal is identified very easily. So there are 4 reasons for choosing tetramethylsilane as the reference compound. The frequency of absorption is different. Tetramethylsilane is highly volatile. The sample can be easily recovered. The reference compound can also be easily recovered. Tetramethylsilane is not reacting with other compounds. TMS has 12 protons, so it can be easily identified. So because of the 4 reasons, tetramethylsilane is used as the reference compound. See, the NMR spectrum is obtained as the output by comparing the signals of the organic compound with the signals of tetramethylsilane in terms of its frequency. So, since we are making a relative comparison, the frequency of absorption of the 12 protons in TMS is assumed as 0. So, the frequency of absorption new TMS is assumed as 0. See, if the frequency of absorption of the reference compound tetramethylsilane is assumed as 0, then we can easily derive a unit called as chemical shift in an NMR spectroscopy. So what is meant by chemical shift? The chemical shift value is actually telling you about the frequency of absorption of a nuclei in NMR spectroscopy with reference to tetramethylsilane. So it is a universal unit. Chemical shift value delta is a universal unit in NMR spectroscopy. The value will not change whether you are recording the NMR spectrum in pulse method or in field speed method. Whether you are recording the NMR spectrum in a magnetic field of 1.4 Tesla or 2 Tesla. Whether the frequency of the external source is 60 Hz, 60 MHz or 100 MHz or 240 MHz, delta value remains the same. So we can say the chemical shift value delta is a universal unit. If you record the NMR spectrum along with the TMS and convert the data, how we are going to see how it is calculated or how the chemical shift unit is derived. So, the chemical shift value is a universal unit. Chemical shift is a universal unit for the frequency of absorption in NMR spectroscopy. It is an accepted unit. It is independent of the magnetic field that is applied or frequency that is used. So chemical shift is indicated by the symbol delta. How do we calculate the value of chemical shift delta? See, I told you the tetramethylsilane signal that is used as the reference compound. So new TMS is assumed as 0. With reference to the signals of TMS, what is the frequency of absorption of other protons in the nuclei? The difference is called as the shift. So the chemical shift delta is given by the formula shift from the standard TMS divided by the oscillator frequency. Whether you are using a 60 MHz instrument, 100 MHz instrument or 240 MHz instrument, like that. See, that unit is multiplied by, that expression is multiplied by 10 to the power 6. There is a reason. See, shift from the standard TMS, that means frequency of the sample from TMS. New TMS is assumed as 0. Frequency of TMS is assumed as 0. From the graph the microprocessor will calculate from the location. So, delta value, chemical shift delta is given by frequency of the sample minus frequency of TMS divided by oscillator frequency into 10 to the power 6. Frequency of the sample minus frequency of TMS, tetramethylsilane. So, divided by oscillator frequency. The difference is new frequency of the sample minus frequency of TMS. It will be of a few hertz only, few hundred hertz or less than 100 hertz. Suppose if the difference between the sample and TMS reference compound is 60 hertz, and if you are using a 60 megahertz instrument, that is 60 into 10 to the power 66, then the value will be a fraction, 60 divided by 60 into 10 to the power 6. That is why if you want to, since we want to have the value in a whole number, we are multiplying it by 10, 10 to the power 6 again. See, frequency of the sample minus frequency of TMS, that will be around, let us assume, for an organic molecule it is 60 hertz, not megahertz, 60 hertz, the difference only. You are using a 60 megahertz frequency, but the difference is 60 hertz. So 60 divided by 60 into 10 to the power 6, that will be a fraction. 0.0050 put, after 5 zeros we have 1, 0.001. So it will be a fraction and it will be a difficult thing. So it has to be multiplied by 10 to the power 6. Since it is 1 in million, you are using the unit, namely parts per million. ppm is the unit for delta, chemical shift value. Because you are dividing it by million, since the value will be a fraction, you are multiplying it by 10 to the power 6. So the whatever may be, the difference is 1 in million. So it is called as parts per million. It is a derived unit. Chemical shift is a derived unit. So frequency of the sample minus frequency of TMS divided by 60, 10 to the power 6 gets cancelled. That is your parts per million. So this is the expression for calculating the chemical shift value. So chemical shift value is a universal unit. It is calculated by the difference in the frequency of absorption of the organic compound with reference to TMS. That is called as the shift from TMS. So it is given by the simple symbol new sample minus new TMS divided by the oscillator frequency. Oscillator frequency is 60 into 10 to the power 6 if it is a 60 megahertz instrument. The value, frequency of the sample minus frequency of TMS will be of a few hertz. So you will get a fraction only 0.00050 zeros. After that you have 1. So it has to be converted into a whole number. So you multiply it by 10 to the power 6. So the unit for delta value is, or chemical shift is, parts per million. So this is about the chemical shift value. See, we have seen how the chemical shift value is derived. Now let us see some of the calculations. See, here I made a comparison for your understanding only. So because of this, since you can see both of the things simultaneously, I have not divided into 2 slides by photo editing. See, the frequency of TMS, that is assumed as 0. In a 60 megahertz instrument, let us assume that the frequency of the sample minus frequency of TMS, it is 0, it is 60 hertz. It is 60 hertz. The compound will show a frequency of absorption at 60 hertz only. Then, see, delta value is 60 divided by 60 into 10 to the power 6 into 10 to the power 6. So if you cancel, the final value is 1 parts per million. So if you convert the chemical shift value into frequency of absorption, it is very clear from the calculation that 1 parts per million is equal to 60 hertz. If the frequency of absorption of the sample is 60 hertz, then only you will get 1 parts per million as the answer, chemical shift value. So 1 parts per million is equal to 60 hertz. Suppose from the spectrum, if the chemical shift value delta is 2 parts per million, then it means the frequency of absorption is 120 hertz. 3 parts per million means 180 hertz. Instead of look at the right side, instead of a 60 hertz instrument, suppose if you are using a 100 hertz megahertz instrument, 100 megahertz instrument, then the frequency, difference in the frequency of absorption is 100 hertz, not 60 hertz, it is 100 hertz because you are using a 100 megahertz instrument. Frequency of the sample minus frequency of TMS is 100 hertz. So delta 100 divided by 100 into 10 to the power 6, again 10 to the power 6 is equal to 1 parts per million. So the same compound, whether it is recorded in 60 megahertz instrument or 100 megahertz instrument, it gives you the same chemical shift value. Delta is 1 parts per million because you are using the expression, namely frequency of sample minus frequency of TMS divided by oscillator frequency. The oscillator frequency also varies. Okay? If you use a 60 megahertz instrument, put 60 into 10 to the power 6. If you put 100 megahertz instrument, oscillator frequency is 100 into 10 to the power 6. So 1 parts per million. But there is an advantage. Instead of using a 60 megahertz instrument, if you use a 100 megahertz instrument, then the spectrum will be clear due to high resolution. The excitation process will be very clear and you can record the NMR spectrum with very high resolution. The signal will be very clear. So the delta value of the NMR spectrum, the nuclei in the NMR spectrum can be easily identified and calculated. The delta value is expressed. Some of the authors are preferring this unit also. Delta value, delta symbol delta unit is used by another unit also, that is called tau. In some of the books, that unit is referred. Both are same. Tau and delta are related by this equation. See, tau is equal to 10 minus delta parts per billion. It has to be subtracted from 10. Later on, we are going to see the chemical shift positions for the protons. See, for normally all the protons are showing a chemical shift value in the range say 0 to 10 parts per million only, not more than that, very rarely. 1 or 2 protons are showing a higher chemical shift value, that is above 10, 13 parts per million. That is very, very rare. Protons in a highly de-shielded environment, for example, keto-enol tautomerism. The enolic proton is hydrogen bonded. In such rare cases only, protons of carboxylic acid which are hydrogen bonded. We will see one by one how the chemical shift value is affected. So, the delta value is expressed by another unit, namely tau. Tau is 10 minus delta parts per billion. So, this is about the chemical shift value in NMR spectroscopy. So, in the next class, we shall see what are the factors that are affecting the NMR spectroscopy. So, today, in this class, we have seen how the NMR spectrum is recorded by 2 methods, namely field sweep method and pulse method, how the data is accumulated, what are the confusions in NMR spectroscopy, NMR data due to the different methods of recording NMR spectroscopy. So, we saw the requirement for a universal unit. The universal unit is your chemical shift value, how the unit is arrived. The chemical shift unit value is calculated with reference to a compound, namely tetramethylsilane. That compound is called as the reference compound in NMR spectroscopy. We saw the reasons for choosing tetramethylsilane as the reference compound in NMR spectroscopy, and we saw the calculation how the frequency of absorption of an organic compound, the protons of an organic compound is recorded with reference to TMS, and how the chemical shift value delta is calculated automatically by the instrument itself and how it is plotted. So, with this I conclude today's lecture. In the next class, we shall see the factors which are influencing the chemical shift value in NMR spectroscopy. So, with this I conclude. Thank you. Let us meet in the next class.